make it. Come with the weak shit, I break it. Step into my zone, mad rhymes will stifle ya. Lines like rifles go blast when I...
Okay, so we have a tank in the form of an inverted cone with altitude of 16 meters, so altitude meaning height, and radius of 4 meters, has water flowing in at 2 meters cubed per minute. How fast is the water level rising when the water is 5 meters deep? Okay, so there's a lot of things going on. So the first thing, of course, because this is a related rate, is we're going to draw a picture. All right, so this says a tank in the form of an inverted cone, so that means upside down, so like a cone, all right, like a funnel sort of. So here's our cone, something like that, okay, like that. Okay, so something looking to this effect, and then we have the radius. Well, the height is going to be 16, so how tall it is 16 meters, and we know that the radius, so the largest radius is 4 meters, okay, and the water is flowing in, so we have water coming in, right, so the water level is going to be rising, okay, so this is our height. We can consider this our height, so this is h, height, and this is our r, our radius at a given time. Okay, so we have, so altitude is 16, okay, of our entire cone, and the radius is 4 of the cone. And the water part, that's flowing in at 2 meters cubed per minute. So water flowing in, that corresponds to volume. Okay, so the change in our volume with respect to time is going to be a positive, because it's flowing in at 2 meters cubed per minute. Okay, let's see what else we are given. So how fast is the water level rising? So we're asked for the change in water level, so that would be the height. So change in height, we're looking for dH dt. Okay, so that'll be our ultimate question mark, all right? And then what else are we given at the end here is when the water is 5 meters deep. So 5 meters deep corresponds to a height of 5 meters. All right, so let's see what we can do with this. First of all, let's relate our variables in some fashion. So we have, let's relate volume to something of the cone. So volume of a cone is given by 1/3 pi r squared times h. Okay? So this, if we implicitly derive with respect to time, so d dt both sides, we're going to have dv dt. Okay, so we do know that, so that's good, is equal to, I'll just put the pi over 3 all together. Okay, pi over 3, and then we have r squared h. So what can we, if we derive, this looks very complicated, right? Because we're going to have a bunch of r's going on, a bunch of h's, and we aren't even given information about r's, right? So r's are kind of off the board. I don't know where they're even coming from, because at this time we're not given a certain r. So what we can do, because there are too many unknowns, so we're going to kind of scratch what we've done so far, okay? Because there's too many unknowns, particularly the r's. We need to do something with those. So what the trick is for cones anyways, I'll show you the trick on the next slide. So I'll redraw this cone here. Okay, so let's say we have a cone. It's kind of like an ice cream cone, right? But in this case, we're filling it with water. So the overall cone is 4 meters. It has a 4 meter radius and a height of 16 meters. Okay, so what we're going to do is a trick called similar triangles. Okay, so if you look at it, when we have any lower water level than the top, we're going to have a height, right, and a radius. And these create similar triangles. So here's our big one formed by the entire cone. So this is 16 meter side, a 4 meter side. And then what if we have a little triangle, right? The water level isn't up to the top yet. We have an H and an R. Okay, so we can work with the properties of similar triangles. And this is for cones in particular. So the ratio that we can create is an H over R ratio. So height over radius. And if we plug in those values that we know, so for the overall triangle, for the big one, we have 16 meters over 4 meters, okay? So this is going to be constant. This ratio here is going to be constant for the entire cone, because that's just the properties of cones, right? So what we can do is actually solve for r, okay? So if we solve for r, what we can do is like cross multiply, okay? So we get 4, well, the meters can cancel out first of all. So we get 4 times h is equal to 16r. So then if we divide by 16, we get that r is equal to h over 4. Okay? So what this does, we've discovered something quite important here, because remember our formula for the volume, so that was pi over 3 times r squared times an h, okay? So what we can do, because there were too many variables, that was our problem that we ran into, so what we can do with this formula that we just found, this equation here, is actually plug in h over 4 for the r spot. And in doing so, we're going to eliminate that r variable, the radius variable. Okay, so let's do so. So we have v is equal to pi over 3, and then instead of r, we're going to plug in an h over 4, and then squared times h. So see here how we reduced the problem to v's and h's, so volume and height. Okay, so this is going to be, let's see what we have. So pi over, pi over 3 times h squared over 16 times an h is equal to pi over 48 times h cubed. Okay, so that simplifies things a lot. Alright, so let's continue on the next slide. So now we have that v is equal to pi over 48 h cubed, okay? And now if we implicitly derive, so now let's do the d/dt thing on both sides. So we have dv dt, and then on the right side we have this constant pi over 48, and then 3h squared times dh dt. Okay, so again, just a refresher, dv dt, the change of volume, was going to be a positive 2 meters cubed per minute. Sorry. 2 meters cubed. Oh wait, yeah, that was correct. Okay, so 2 meters cubed per minute, and then we know that our h, our instantaneous height, the one that we're studying, is going to be 5 meters. Remember, the water was 5 meters deep. And the last thing that we wanted to find was dHdt. How fast is this water level rising? Okay, so that's fine being an unknown for now. Alright, so let's plug this in and solve for dHdt. So we have dV dt being 2 meters cubed per minute. And then on the right side we have a pi over 48 times a 3. So there's a 3 here. And then an h cubed, so that's 5 meters squared. Sorry, h squared. And then we have that dHdt is just sitting there. Okay, so now this 3 and the 48, those can simplify to a 1 and a 16. Alright, so now we're going to divide by all of this. So we're going to get that dHdt is ultimately going to be 2 meters cubed per minute. And then we have this times the reciprocal of all of this. So that'll just be a 16. So 16 over pi over 5 meters squared. Okay, so something like that. And then this is going to simplify to 32 on top, okay? So we have a 32 meters cubed over, and then we have a 25 pi on the bottom, and then meters squared minutes. And then so this, we can cancel out a meter squared, both top and bottom. So our final answer is going to be a 32 over 25 pi meters per minute. And this again, this is the rate of change, or how fast our water level is rising. So dH dt. Alright, so that wraps it up for this practice problems video on related rates. I hope that helps, and happy studying.
All MCs, when I breeze, give me room, please. I be like fascinating when I be updating, cutting off white kids, pulling their trump cards, I thump hard.